door being dramatically reopened. Today, we're exploring exactly that kind of monumental shift in mathematics. Our deep dive is into how we solve these incredibly complex polynomial equations. For generations, mathematicians, well, they just accepted a fundamental limit to what was possible. But then in 2023, a groundbreaking new method emerged, changed everything.
That's right. We're going to unpack Izzuiti's theorem today. It's a revolutionary approach, really, provides exact symbolic solutions, and not just for some polynomials, but for equations of any degree. You'll see how this theorem kind of bypasses the historical constraints, outperforms traditional methods, too. It solves problems once thought fundamentally, well, out of reach. Our mission. To understand this transcendence, as we're calling it, and explore what it really means for you, the learner.
Okay, let's start by setting the stage a bit. For nearly 2 centuries, mathematicians lived with this profound constraint on solving high-degree equations. Can you tell us about that foundational work? Why was it such a barrier?
Absolutely. Yeah, the story really begins back in 1824 with Niels Henrik Abel. He etched his name into the mathematical canon, didn't he, by proving what we now call the Abel-Ruffini theorem. And this theorem basically stated that there's no general solution in radicals for polynomial equations of degree 5 or higher.
Radicals meaning things like square roots, cube roots.
Exactly. Square roots, cube roots, those kinds of operations. Abel proved you couldn't make a general formula using only those for degree 5 and up. And this wasn't just identifying a difficulty, it was. You could call it an intellectual closure. It slammed the door shut on finding exact formulas for degrees beyond 4 using those tools. So mathematicians had to turn elsewhere, numerical approximations, perturbative methods, iterative solvers. That became the norm.
Right. So if direct, exact solutions were off the table for these higher degree equations, they had to find workarounds. But I imagine these alternative methods came with their own set of headaches, didn't they? What were the big trade-offs there?
Oh, they certainly did. Yeah, the primary drawbacks are things like instability, rounding errors. When we say exact, we mean a precise symbolic answer, right? Not a decimal approximation that might be close, but still has some error baked in. Numerical methods, well, by their very nature, they give you an approximate value. They just can't give you the true symbolic form. So for high-degree polynomials, say NO5, the classical methods simply fail to give a general exact solution.
That really clarifies the historical challenge. Okay, so Abel's theorem set these boundaries. Then what changed? Because something truly remarkable did happen in 2023. Murad Sultan Izzuiti introduced this breakthrough method, completely redefined the landscape. How does Izzuiti's theorem manage to do what Abel's theorem seemed to deem impossible?
Well, what's fascinating here is that Izzuiti's theorem doesn't actually contradict Abel's theorem. It doesn't break the rule. Instead, it transcends it. Remember, Abel's theorem is specifically about solutions and radicals.
Ah, okay. That specific tool set.
Exactly. Izzuiti's approach surpasses these traditional radical expressions because it operates in, let's call it, a richer symbolic space. It achieves what was once thought mathematically impossible by using a clever technique. It involves recursive power sums, complex exponentials, and these deep recurrent structures within the polynomial itself.
So it finds hidden patterns.
In a way, yes. Imagine it like this. Instead of brute forcing, the theorem builds up the answers systematically using patterns derived from the polynomial's coefficients. This allows it to deliver exact, symbolic, closed-form solutions for polynomial equations of any degree.
That's a powerful distinction. So let's zoom out a bit. How does Izzuiti's approach stack up against all those traditional, maybe numerical methods we just discussed? What are the key differences the listener should really keep in mind?
Yeah, that's an important question, and the distinction is pretty clear. Let's break it down. First, the degree limit. Classical methods, as we said, hit a wall at degree 5. Izzuiti's theorem solves any degree. We're tackling a 19th degree today, but it could be 100th, 1000th.
Wow, okay. Big difference there.
Huge. Then there's the root form. Classical methods give approximations, or radicals, but only up to degree 4. Izzuiti's provides exact symbolic expressions, often using things like complex exponentials.
Meaning you get the actual answer, not just close enough?
Precisely, the true mathematical value. Then, error handling. Classical numerical methods, they inherently introduce numerical instability, rounding errors. It's unavoidable sometimes. With Izzuiti's theorem, 0 error. It's purely symbolic precision.
That's crucial for many applications, I bet.
Absolutely. And finally, generality. Classical methods are often limited to specific solvable forms. Izzuiti's theorem is universal. It works via this recurrence and structure analysis.
You mentioned earlier it could even make numerical guesswork obsolete and outperform AI systems. That's a bold claim. Are there any scenarios where traditional numerical methods or even AI might still have an edge? Or is this really a complete game changer across the board?
That's a fair point. Look, Azuide's theorem provides exact symbolic solutions, which numerical and AI methods by design often don't aim for or can't achieve. Those other methods still have their place, absolutely, especially when an approximation is genuinely good enough for a particular task or maybe for speed on certain types of very large, less structured problems. But for finding exact solutions, especially for these high degree polynomials where radicals fail, yes, Azuide's theorem really does render the old limitations, that reliance on guesswork, obsolete. It's a fundamental shift.
Okay, let's make this concrete. To truly grasp the power here, we're going to tackle, as you said, a beast of an equation today. A 19th degree polynomial. That means it is x raised all the way to the power of 19 complex terms. Just looking at it as a string of numbers and powers that would normally make your head spin. We won't list every single coefficient, it's quite long. But the equation starts by 19 by 18, and goes on with many large coefficients, ending 20 by 831355 equals 0. It's monumental.
It really is. And traditional methods for solving something of this magnitude, they'd rely heavily on numerical approximations. Methods like, say, Newton's method would give you approximations, but again, you run the risk of rounding errors. You can't guarantee the exact values. With Azuide's theorem, we approach it completely differently. We're solving for the roots symbolically, precisely.
Right. So how does Azuide's theorem let us break down this specific, intimidating 19th degree polynomial? How do we find those exact roots without approximation? Give us a sense of the process.
Okay, so the method, it involves this recursive process. It systematically finds the exact values of the roots. We start by expressing the polynomial in terms of these special symbolic coefficients. Let's call them scar. You can think of these scars sort of building blocks. They're derived directly, recursively from our original polynomial's coefficients. Instead of getting bogged down in the huge numbers right away, Iswidi's method lets us work with these scar symbols.
Okay, symbolic building blocks.
Exactly. And the key is that every single scalar coefficient is determined symbolically. No numerical approximation creeps in at this stage. We calculate these scalar values for each degree, from 0 up to 18 in this case. Now, here's what's truly fascinating, and it's a major simplification for this specific polynomial. When we calculate these scalar coefficients recursively, an astonishing number of them just vanish. They turn out to be 0.
Wait, really? 0? How many?
A lot of them, specifically SIR through S7R, then skipping a couple, SENR through S16R, and even S18 are all 0. And this isn't just luck, it's a property of the underlying structure of this particular polynomial that Azuide's theorem is able to reveal and exploit. It effectively strips away layers of apparent complexity.
That sounds like a dramatic simplification.
Yeah.
Is that common for polynomials with Azuide's method, or is this particular equation just, I don't know, uniquely suited for that kind of collapse? And which coefficients aren't 0 in this case?
Well, it's not guaranteed that every polynomial will simplify quite this dramatically, no. But the power of the theorem is that it provides the framework to find and use these hidden structures when they do exist. And for this 19th degree beast, precisely, only 2 key coefficients are non-zero, S at R and S17R. And we can calculate their exact symbolic values. S at R is 923,77,199, and S17R is 923,731,1918. Still big numbers, but symbolic and exact.
Okay, so only 2 non-zero scalar values matter out of 19 possibilities. What does that do to the equation?
It simplifies it enormously. Because of this, the entire massive 19th degree polynomial px collapses. It dramatically reduces to just this. Px equals x times by 18, a scale by 9 plus s17r equals 0.
Well, okay, so you could just factor out an x.
Exactly, which immediately tells us that x must be one of the exact roots. Simple as that.
That's one root down. What about the by 18 a8r by 9 plus s17r part? That still looks complicated.
It looks it, but look closely. Let y equals x 9. What does that equation become?
No, y2 a8ry plus s17r is 0.
Precisely. It's just a quadratic equation, but in terms of by 9.
That's the aha moment right there. So you're saying this monstrous 19th degree polynomial, which used to require error-prone approximations, can be broken down into a simple x row and then something that behaves just like a high school quadratic equation, using those exact symbolic scalar values.
That's exactly what I'm saying. We can now solve for by 9 using the familiar quadratic formula, plugging in the exact symbolic values we found for 2psi-r and S17r. No approximation needed.
So it's almost like finding this hidden quadratic structure within the 19th degree equation.
Yeah.
That's truly elegant. What makes that possible? Is it just this theorem? And once you have the values for by 9, how do you get back to the final x roots?
Yes, it's the theorem's ability to uncover these underlying recurrence structures that makes it possible. By expressing the problem in terms of scale and then seeing that most are zero, the original beast reveals its much simpler core. So we use the quadratic formula to find the two exact symbolic values for by 9. Let's call them y1 and y2. They'll look like never s8r plus scort s8r2 for s17 2. Then the final roots for x are obtained by taking the ninth root of y1 and the ninth root of y2.
The ninth root, so that gives multiple complex roots for each y value.
Exactly. Taking the ninth root of a complex number yields 9 distinct complex roots. So the 9 roots from y1 plus the 9 roots from y2 plus the x area we found earlier, that gives us all 19 exact roots. And these roots are expressed elegantly using complex exponentials, providing all 19 roots in their precise symbolic form.
Incredible. No guesswork, no rounding.
That's the crucial point for you to remember. Izuti's theorem provides a precise symbolic solution. The roots we derive are exact. They aren't subject to the errors you get with numerical methods. This approach ensures we can find the roots exactly, even for these incredibly high-degree polynomials that classical methods just couldn't handle exactly. The recursive structure guarantees a systematic and precise derivation.
So what we've really unpacked today, it's nothing short of a paradigm shift, isn't it? We've seen how Izuti's theorem doesn't just offer a new technique for high-degree polynomials. It genuinely redefines what's possible. It moves us beyond those centuries-old limitations set by radical solutions.
Absolutely. And this specific work, detailed in what's known as the 49th volume of the theorem's development, where this 19th degree polynomial was solved, it's more than just a mathematical result. You could see it as a philosophical statement. It demonstrates that exact symbolic solutions are achievable for any polynomial degree. It really does render numerical guesswork obsolete in many areas where precision is key.
For you, the learner, this deep dive really shows that even in fields as established, as old as mathematics, the impossible can become transcendent. All it takes sometimes is a completely fresh perspective, a new framework. Which leads us to our provocative thought for you to mull over. If a door that everyone thought was locked and bolted for 200 years can suddenly be reopened in mathematics, what other long-accepted impossibilities, maybe across science, technology, or even in our everyday challenges, might just be waiting for a completely new way of thinking, a totally different framework to emerge?